Well, hello again, and welcome to another session of Rockville High School Chemistry's distance learning. Today, we're going to talk about thermochemistry. This lesson is for the week of April 27th to May 3rd. There are two assignments due this week, and you can look on Google Classroom or email me to get any other questions answered. They are both due on the 3rd of May. The first assignment is a calorimetry virtual lab, and that's a completion assignment worth 10 points. There's a presentation that will help you with the virtual lab. That's another presentation which you can find on Google Classroom. The link is also in this presentation. The second assignment is a calorimetry practice problems, and that's 10 points. These questions will be graded, and you can review and change your answers up until the due date, which again is the 3rd of May at 11 p.m. Some key terms and equations for today's lesson are calorimetry, calorimeter, enthalpy, thermodynamic equilibrium, the ideas of endothermic and exothermic processes. The objectives for this week are similar to last week. We're still focusing on the idea of the law of conservation of energy and the flow of heat. Today's lesson is an application of the law of conservation of energy, and that's something called calorimetry. Calorimetry is the science of measuring the heat of chemical reactions and/or physical changes. We can also use calorimetry to determine things like the specific heat or the mass of a substance. We can also use it to determine the amount of temperature change for a substance or the energy transferred, Q, in a process. So calorimetry is a fundamental, important idea in thermochemistry. So in calorimetry, an important idea is that the heat released by the system is equal to the heat absorbed by the surroundings. And we can say conversely that the heat absorbed by a system is equal to the heat released by its surroundings. It's really important in calorimetry that the system be isolated. Now, what does it mean for a system to be isolated? Well, let's look at a couple of examples. This is what we call an open system. And in an open system, you can see that both energy, which is represented by the red arrows, and matter, which is represented by the lime green arrow, can exchange from the system. If we think to last lesson, where we looked at heat flow and we used a hot cup of coffee as an example, an open system would be a hot cup of coffee with the lid off. Now, a closed system, well, that would be a hot cup of coffee with a lid on. And so the coffee can cool off, but the coffee is not going to leave the coffee cup on its own. And lastly, we have what's called an isolated system. And that's where neither energy or matter can escape or enter the system. And that's the ideal calorimeter, an isolated system. Let's look at a couple more definitions. What exactly is a calorimeter? Well, it's an object used for measuring calorimetry, or the process of measuring the heat of chemical reactions or physical changes, as well as heat capacity. Think thermometer, but instead of measuring heat, it's measuring energy. There are a bunch of different types of calorimeters. Here's a picture of a couple. The one on the left in figure A is a calorimeter with a thermometer, a stirring bar, and some insulation around the cup and a lid. And the one in figure B is a little bit more precise. It's got a temperature probe, like the vernier temperature probes that we used in class, that's attached to a Chromebook and a motorized stir, and again, insulation around the sides and on the top. The type of calorimeter that we would use in a high school lab is typically something like this, and it's called a coffee cup calorimeter. Now, coffee cup calorimeters actually do a pretty good job because styrofoam as you know from styrofoam coolers, are pretty good insulators. So for the purposes of a high school chemistry lab, a coffee cup calorimeter does a pretty good job. So what are the basic concepts that apply to calorimetry? Well, number one, it's an application of the law of conservation of energy. Second, we need to know what is the system and what are the surroundings, and ideally, those two are isolated from the universe around it. And also is the idea of thermodynamic equilibrium. That is to say that when two things reach the same temperature, there's no heat flow. Oh my goodness. Let's do some calculations or talk for a minute about some calculations in calorimetry. And this is just a review of what we said in the previous slide, that in calorimetry, the heat released by the system is equal to the heat absorbed by its surroundings. And conversely, the heat absorbed by the system is equal to the heat released by its surroundings. Well, that's a lot of words. Let's take those words and put them into an equation. Not this type of equation that we're looking at. Another equation that we're a little bit more familiar with. We can say that Q is equal to enthalpy. Q is sometimes equal to delta H. That's the equation that we're looking at. Q is equal to mCp delta T, where m is the mass, Cp is the heat capacity, and delta T is the change in temperature. Now, delta T we define as the change in the final temperature, we define delta T as the final temperature minus the initial temperature. We can also recall from the given equation for enthalpy. Oh, that's right. Let's look at it and let's look at an example here. So here's an application of the calorimetry equation. We have some hot metal and cold water, 150 grams of water at 25 degrees Celsius, and 71.9 grams of metal at 100 degrees Celsius. So it's important whenever we're doing calorimetry calculations to know the mass of something and the initial temperature of something. So here we put the hot metal into the cold water, and the metal releases energy to the water. And at some point, those two, the metal and the water, reach a thermodynamic equilibrium, and we measure that temperature. And in this example, the final temperature is 28.6 degrees Celsius. Now you might ask, well, is that the final temperature of the metal, or the final temperature of the water, or both? Take a moment and think about that. The answer is it's the final temperature of both, because they are at thermodynamic equilibrium. Well, when we take our results or our values of temperature and mass that we measured, we can figure out the amount of heat that went into the water. We use our equation, Q equals mCp delta T, and we know that the mass of the water was 150 grams. The heat capacity for the water is 4.184 joules per gram per degree Celsius. That's a constant and given in any of these calculations. And the change in temperature of the water is 28.6, or the final temperature, minus 25 degrees, the initial temperature, or 3.6 degrees Celsius. When we plug those values into our equation, this is the answer we get. First, keeping track of our units, we see that grams and grams cancel out, degrees Celsius and degrees Celsius cancel out. And when we multiply these values together, we get 2,259 joules of energy went into the water. Well, okay, we would like to know how much heat left the metal. Take a second and think about that. Because of the law of conservation of energy, and because a good calorimeter is isolated from the system, we can say that the energy that went into the water is equal to, but opposite to, the energy that left the metal. And that allows us to do other calculations. In reality, some of that heat left the calorimeter. no calorimeter is 100% isolated. And so in our example, some of that heat would have left the calorimeter and went into the room. We can use the idea that the energy that left the metal is equal to the energy that went into the water to figure out the heat capacity of the metal. Well, how would we do that? Pause the video, take a second, and try to answer that question. If we look at our equation, Q equals mCp delta T, we see that we can solve that equation for heat capacity thusly. And we could say that C sub P is equal to Q divided by m delta T. We know what the Q for the metal is because we know what the Q for the water was. The mass of the metal was 71.9 grams. The change in temperature for the metal, 28.6 degrees minus 100 degrees, or negative 71.4 degrees Celsius. Plugging those values into our equation, we get a heat capacity of 0.440 joules per gram per degree Celsius. And when we take that value, we compare it to a table of specific heat capacities, we can figure out what metal it was that we placed into the water. In our example, that was nickel. So as a review, there are 2 assignments that are due this week. Look at Google Classroom. Email me if you have any questions. The first one is the Calorimetry Virtual Lab. There's a presentation to help you with that assignment. And lastly, there are some calorimetry practice problems. These questions will be graded. You can review and change your answers until the due date, which is the 3rd of May at 11 o'clock. Now there's a couple of calorimetry practice problems. If you'd like to, you can pause the video now, print out these calorimetry practice problems, try them, and compare your answers. I have the answers on this video. So that concludes this portion of the video. I hope you enjoyed it. Email me with any questions, and I look forward to talking to you on Tuesday or Wednesday.